Okay, so good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. As you probably all know, NITheCS is the national institute that is emerging out of the good old National Institute for Theoretical Physics, and it opened up the doors also to other interesting teams. Yeah, and sorry, I forgot to mention who I am in case you don't know it. My name is Francesco Petruccione, and at the moment I'm the interim director of NITheCS. Yeah, this afternoon we are very happy to have with us Dr. Deshen Moodley. Yeah, and Deshen is a brand new associate of NITheCS. Yeah, but his main job is at the University of Cape Town, where he's an associate professor in the Department of Computer Science. And Deshen is also the co-director and the co-founder of the South African National Center for Artificial Intelligence Research, CARE. Yeah. Before joining UCT in 2016, for a dozen years or so, Deshen was an academic in the Computer Science Department of the University of KwaZulu-Natal, where we were colleagues for several years, and that's where we also met originally. Yeah, and today Deshen kindly agreed to speak about his recent work, and the title of his contribution is Designing Adaptive and Cognitive Computer Systems in South Africa. So Deshen, thank you so much for being with us this afternoon, and we are very much looking forward to your talk. And in particular, I'm very much looking forward to listen to a non-theoretical physics talk, yeah, because that is something to which we all need to get accustomed now. So please take care that maybe some of the audience might not be trained in computer science too much. Yeah, so we are really very grateful that that you made the effort to be with us this afternoon. And Deshen, if you would like to start sharing your screen and start with your presentation, you're more than welcome to do so now. Yeah, and as usual, the rules of the games are: if you have questions, please use the Q&A facility, which is in the right bottom corner of your Zoom screen, and Professor Sinaisky will moderate the questions at the end of the talk. So Deshen, if you would like to start, it is your show, not mine.
Thank you very much, Francesco, and thank you for inviting me. So good afternoon, everyone. I'll be talking about some of the research that I've been doing on adaptive and cognitive systems, and I'll give you a flavor of some of the work that we've been doing in the group. As Francesco said, I understand that there's people with different backgrounds, and you might not necessarily have a background in computer science. So just to introduce some concepts. So a system, architecture, and framework, and this is some of the concepts that I'll be talking about. So the area that I work in is about developing complex and large-scale computer systems. And these systems are quite challenging to build. They're not very established in terms of how to design such systems. And when we design a system, we talk about the architecture of the system. A good way to think about architecture is in the general sense, when there's architects who design houses and they come up with the architecture of a house or a building. And interestingly enough, a lot of the terminology, for example, architectural design patterns, actually comes from the discipline of architecture. So the architecture of a system, it specifies the system components and how these components, the different components in the system, interact with each other. So in some sense, it's an abstract blueprint of the system. And especially for complex systems and systems that are difficult to build, this is really helpful for teams of developers that will be working on the systems in terms of extending it and maintaining it. So this, they all know which component they work in, and which component this component interacts with. So if there's any knock-on effects or things that need to be tested. So the idea of design patterns or architectural design patterns, these are kind of tried and tested guidelines or blueprints that can be used to solve particular problems. And architectural design patterns, or if you want to use the word well-known architectures, they form almost like a body of knowledge in the community. So when you see a challenging problem in terms of system design, you can find the one, and based on your experience and knowledge of these design patterns, you can work them out and modify it for your for the system that you're currently creating. It also, beside these kinds of blueprints, it also it performs or provides a standard vocabulary and a way about talking about this design endeavor. And again, when you develop a computer system, especially these large-scale systems, there's a lot of design, and in some sense, it's also a creative task to invent or create something. So a framework, it includes the architecture, the tools and the methods for building these software systems. So you have to, not just the architecture, also there might be some development tools and also some methodologies or methods for building software. So in this notion of intelligent systems, one of the paradigms or software engineering paradigms that is often used, and it's been around since the early 2000s, is the notion of an intelligent agent. Typically it denoted a autonomous, and again, the word intelligence is a bit loaded, software component. It was a large-scale software component. So in the same way, a lot of you would have probably heard of object-oriented programming, where you look at and model objects in a software system. Agents-oriented programming, where if you want to call it a more higher scale software component, which had some autonomy, could learn, could provide some reasoning or cognition similar to humans. And this is the notion or the paradigm of agent-oriented programming. So again, just as in the architecture and the frameworks, it provides common techniques and standard terminology to analyze and compare these sorts of systems, where you're designing a software agent or a system that has multiple agents or a multi-agent system. However, when we talk about intelligent systems, we might not always talk about systems that are agent-based. So there are intelligent systems that are not agent-based, explicitly called agents, but they might have a lot of these properties of agent-based systems. And again, intelligent, when you talk about intelligence, it's a loaded word, but it's a big philosophical issue about what is intelligent and how do you confer or characterize the intelligence or the degree of intelligence of a computer system. That's quite philosophical, lots of contention about it. But for this talk, we consider it to be how sophisticated the mechanisms for autonomy, self-learning, adaptation, and cognition. And we'll use that as the more sophisticated these measures are, we will confer or characterize the system as being more intelligent. So the systems that I work with I just want to bound it because it's not just arbitrary systems. It's computer systems that are observing or working in some environment. And I call this a task environment. And the work that I've done is mostly been on observing physical systems and some virtual systems, but generally physical systems where there are sensors deployed in some physical system and there's observations coming through. So some of the characteristics, it could be this physical system could be unknown, partially observable. There could be a lot of uncertainty. The underlying processes which govern the systems may not be well understood. And observing the system, by observing these physical systems, we continuously improve our understanding. The system, again, just to repeat, that it's an evolving and dynamic environment, and the underlying processes, even if we do understand that they could suddenly change, and especially, like, for example, our natural environment. The observations emanating from these, they could be multiple sensors, and these sensors could be, different manufacturers could, and they could provide information observations in different formats. So it's heterogeneous and it's continuous. So we're always receiving data from these sensors. Some of the issues we could have: interoperability, different formats of the data, different protocols that the sensors use. And there could be noise because of sensor error, and again, the erratic environment. And they might also be, besides just observing these systems, we might need to also determine whether we need to intervene or take action in these systems. So broadly, the challenges, I mentioned interoperability. There could be heterogeneous sensor data. The other two that I want to point out is knowledge dynamism. The things that we observe in the system. So as new sensors come on board, we could have new things, or probably sensing things or observing things at a higher resolution than we could before. So new observables, more refined observables, measurements, knowledge models, situations in the systems, all of these can evolve. And our understanding of these systems also evolve. So we need to, so one of the challenges is some mechanism to update the agent's knowledge when these things change. And how do we build these data-driven models? And again, I'll talk a bit more about the use of machine learning to do this in these environments. But beside the knowledge, the environment changing, our understanding of the environment changing, the sensors we deploy, also the system that observes this, that could also change, because we might be new things that we need to take decisions on. That's also an evolving thing. It's a complex system which we think is persistent, it's long running. So the computer system itself can change in terms of what we expect from it and how it works. So I like visuals. So maybe just to put that, to sum that up. So there's some bounded physical environment. There's sensors monitoring something in this environment, and there's lots of things that we could monitor both inside this house and probably in the external environment. There's also some humans here, so we could monitor human activity. And then we have some monitoring functionality. We could monitor the situation with the air quality inside and outside of the house, the weather, and also what the humans are doing in this bounded physical system. But it doesn't always need to or have to be a physical system. It could be a virtual system, but again, it should be bounded. And two examples here of virtual systems is, let's suppose that the environment is a retail store, and we're very interested in the purchases we track. So you've seen like loyalty cards where we're tracking purchases of what people buy, for example, at Woolworths. And maybe we're interested to see what trends are being emanating, or what's happening. And we see there's an increased demand of vegetarian meals, because now I think people are moving to become vegan or vegetarian. And then we have to take some intervention, possibly stock up on this for the increased demand, or develop new products to cater for this increase in demand. Another example is the stock market, and we could be monitoring share prices. And what we're really interested in is situations where there's an overvalued or undervalued share, and then we'll decide to buy, hold, or sell shares accordingly. So again, it's an environment, some sensors with observations, and then we do kind of analysis of these observations, prediction, and possibly some decision making. So that's a brief idea of the types of systems and in terms of the work that we've done. And I'm going to take you through 4 applications and in the sequence that they occurred, because these generally they've been developed incrementally and they build on each other in terms of creating these sorts of architectures to support these decision-making in systems. And the first one was very early work about 10 years ago in the sensor web, and then worked a little bit with biodiversity data, and then an application on indoor air pollution monitoring, and then more recently on monitoring domestic electricity consumption in South Africa. The techniques that I've used initially was ontologies and agents as a modeling paradigm. And then towards the end of this research, I saw the need to use these entities called Bayesian networks, which I'll speak a bit more about later. And then I continued with that. And then more recently, there was some machine learning and some both and cluster analysis, which I'll talk about. Okay, so the first application scenario was work built on something called the sensor web. And the Open Geospatial Consortium is a standard space organization in the geospatial space. And they come up with not just data standards, but also services for processing distributed geospatial data. It's called the Sensor Web Enablement, and this is at that time in 2013. This was the state of the art in terms of how people build distributed geospatial data processing services. So the work here was on something called the Sensor Web Agent Platform. Was to take these kind of services-based software components and elevate them to intelligent agents, to the intelligent agent level, and to see how architectures for agent-based systems could help with dealing with some of the challenges. The challenges here was interoperability in distributed geospatial data. We looked at knowledge representation and reasoning, encoding expert knowledge. And also this was a worldwide scale system, and that was sensor web. So it was at a very different granularity in terms of complexity. So the Sensor Web Agent Platform, it proposed 2 key components, an architecture, agent-based architecture, and a semantic infrastructure using these things called ontologies and Bayesian networks. So this is just to give you a flavor of the architecture. I'm not going to go into detail, but this is how a typical abstract architecture diagram. This is a layered architecture, so there's 3 layers, and the idea is that lots of the data processing happens here. It puts it in a standard format. So if you have data services or sensor data services using different protocols and formats, then this is the kind of mediation layer. And then when it goes to the next layer, it's all in the standard format. And you use standard protocol query languages to access the data. Here, it's more like the processing or analysis layer. We call it the knowledge layer to apply some knowledge to it. And then the applications where you can actually use the things that you processed to construct applications. On the semantic architecture, there was these concept ontologies at a very weak notion. If you don't know what ontologies are, you can think of it as a class hierarchy or concept hierarchy. And of course, it's a lot richer than that. So you can express quite complex logical relations between concepts or things or entities and their properties. And here we realized that on the logic-based reasoning side, we could capture classes and properties of entities, but the uncertainty element was missing, and you couldn't really represent causal relations, so we incorporated Bayesian networks. And Bayesian networks are, you probably heard about the use Bayesian inference, and Bayesian networks are where you relate variables or events in terms of causal hierarchies. And I'll show you an example of that in a little while. Okay, so there's the what we actually used it for. We used it for wildfire detection. So the sensor layer we used, we acquired data from the MSG Severi sensor. It was satellite imagery, so it was brightness, temperature images, the sensor layer. At the knowledge layer, we actually just looked at this as gridded data, and we wanted to extract temperature hotspots. And then once we had temperature hotspots, then we could infer to what extent was this temperature hotspot an actual wildfire. So there's a very simple Bayesian network. So it's a causal relation. If there is a wildfire, it causes a hotspot to occur, and then you should see high thermal variance and values, the absolute value and also the variance in terms of previous readings in that area. So there's the causal, these arcs are causal relations in this graph. And there's conditional probabilities, so you can actually do propagation of uncertainty all the way through here, and you can actually, given a particular value here and here, you could predict what's the chances of there being a hotspot and what's the chances of there being a wildfire. I'm not going to go into any more detail about that, but I can give you the reference for the paper if you need more details about that. So the findings is that from this research was that dynamic data fusion is possible because there was heterogeneous data, multiple satellite imagery, and we also did other applications. The higher level analysis to support decision making, we realized was context dependent. Towards the end of the research, we realized that propagation of uncertainty was crucial, and we introduced Bayesian networks, like I showed you, and also that the decision-making systems was not the endpoint, autonomous decision-making systems. It was about decision support, which is, it's a recommendation to a human user who will then vet this and then decide to take action. Adoption of standards, so in terms of this being a standard architecture, there's a lot of work. So even if you have the most advanced and sophisticated architecture which solves lots of problems, there's a whole new process of actually promoting adoption of these things. So the next application was on in the biodiversity area, and here we wanted to develop a framework for data mining of heterogeneous biodiversity data stores. And specifically, there were 3 museums in South Africa which had these specimen databases. There were 3 natural history museums, and it was about the flower visiting insects. So specimens of these and their behavior when we caught. And scientists in this area use it to create pollination networks, and they're very interested in what the insect was doing when it was visiting the flower. This was Willem Kutz's, one of my PhD students, his project, and he had this, he had lots of knowledge about biodiversity. So the idea was to try and see to what extent we could analyze how scientists in this area worked, and to what extent we could formalize their knowledge and the process they follow and encode it in a computer system. So there were some things that we came up with that were important. So these data sets had lots of missing data. There was certain kind of implicit knowledge that they used when they were interpreting the data, and also to make higher level conclusions. So we attempted to capture all of this and that's the system that we created. So here's an example of data stores, the 3 museums, the Albany Museum, the Zico Museum, and the Plant Protection Research Institute. And you'll notice, like, for example, the sampling method, one says that it was just flowers, the other one was more detailed, and something that was not obvious to a machine. If it sees hand-net, it wouldn't know how to connect this. There was some missing data, and this was just to give you a sample of what the data looked like. So as part of our design, we realized that there was a monitoring of an individual organism or insect, and something that the insect did in relation to the flower, which was an event. And then we could classify the event into some situation of what actually we think happened, and then classify some behavior of that insect, and then aggregate the behavior of multiple insects of the same species, and then use that to infer that this was a more larger scale ecological interaction that occurred for the community of these insects. So that same kind of process, now we had to put it into a computational system or architecture, and we used that to a 3-layered architecture like you saw before. One was to mediate between these heterogeneous databases, and then also to find these individual events. Then it was to detect the situation, what behavior actually we think the most likely happened. And then, of course, the higher level ecological interaction, where we use a few samples to infer behavior of larger ecological communities. So this is a typical ecologic interaction network. I don't understand it fully, so Willem, my student, knows what's going on. But from what I understand is that these green blocks are the insects. In this case, it's oil collecting bees. These blue blocks are the plants, and these are the interactions. And where you see a double diamond, it means that we think that an actual pollen transfer event took place. Apparently, pollen transfer is very hard to know that it actually took place definitively. So some findings, or what we learned from this is that incorporating Bayesian networks really helped us to do high-level situation analysis and abstract reasoning. We found that domain experts responded much better to the Bayesian networks than the ontologies. We initially tried with ontologies, but they seem to respond much better to Bayesian networks. It was aligned with the way they do things. And we produced we managed to automate. We got good feedback in terms of the pollination network that was actually produced automatically by the system when we engaged with scientists in this area. So this is the actual Bayesian network. I'm not going to go into detail. It's just some events and some things that I inferred, and eventually some behavior in terms of what behavior actually took place. So a high level of automatic integration can be achieved to produce these enriched events and behavioral interactions. It's also was more consistent because we could, it was the same process repeated objectively, and also experts could trace back to exactly which observation yielded which interaction. So it was traceable and explicit, and as I mentioned, there was lots of feedback from the experts. So the third application was on indoor air quality monitoring, and here it was monitoring 3 low-income households in South Durban. So this is an area where residents have had a history, a long-term history of CDCF pollution. I think there's some refineries and heavy industry situated in that area. And we wanted to monitor the indoor air quality, and the particulate matter was PM10. This was the pollutant that we were monitoring. It was part of a larger study, and also my PhD student, Jude Adeleka's PhD project. So this is pretty much, there were 3 households, and we were taking PM10 readings at 1-minute intervals. We collected data for 1 week per site, so it wasn't a long-term study. There were more expensive monitoring stations set up at various households, but that was too expensive. We used low-cost sensors, which used a Raspberry Pi and some off-the-shelf sensors. And then those sensors were installed at each of these households, and then it was sent to a server, and then we collected all these data points. And in terms of the abstract, again, a 3-layered architecture and some data or monitoring observations at the lower level. We analyze the situations. Again, you can see it's very similar to the ecological one. And then some decision-making, higher level processes, control and decision-making happening at the top layer. So this looks very simple, and this looks horrendous about lots of things happening, and this is the technical detail. So you had all these observations coming in. We had to classify them as good or poor. There's the threshold, and then we could use some queries using this Sparkle query language, which also relied on the ontology to find out what's the situation. And then we also fed that into a machine learning model, which was updated. I think it was every 6 hours. And then that was also able to predict what was going to happen in the next 30 minutes and the next hour. And based on this, we would then decide whether to do anything proactively, like close a window or open a window and so forth. So we created this concept ontology, which we could reuse for air quality monitoring. And here you could see we use this air quality or environmental quality index to decide whether it was poor or in terms of quality. We were able to analyze the observations and measurements, and then take, depending on the situation, we could take some activity to mitigate any poor air pollution situation. I'm not going to go too detailed into that. On the machine learning side, we incorporated some predictive models, and here this is just to give you the precision recall and specificity. And here it was about what's the lagged values that we were putting into the model. So if we were just putting the previous point in and predicting the next point, then that's what we would get. If we were using 10 lagged values, then you can see that initially, as we increase the number of lagged values, then the accuracy dropped, the prediction performance dropped, and then after around 20, it started picking up again. But of course, the recall dropped. So that was just to give you an idea of 30-minute and 60-minute predictions. We tried a bunch of classifiers, and we found the multi-layered perceptron yielded the best performance for both 30-minute predictions and 1-hour predictions. Of course, it's intuitively 1-hour predictions were performed worse than 30-minute predictions. So here we combined machine learning and ontologies for predictive analytics, and for coping with streaming data in the sensor web. And this it was also, previously it was just ontologies and Bayesian networks that we were using in our systems. It was more the knowledge representation and reasoning type techniques. And here we introduced machine learning. And we saw that it helped a lot with the kind of predictive side. So the most recent application was on domestic electricity consumption. And this was work done from about 2018, I think it was, onward. And this was a bit different from the previous applications. So just some background. This was work in terms of helping energy planners in South Africa understand and predict daily consumption behavior in households throughout the country. So they use something called representative daily load profiles. And all of this is they say for a particular household, like let's say in this diagram, it's a lower middle income household in KwaZulu-Natal, and it has 7 years of electricity supply. Then at different times of the year, in summer on a Saturday, it has this kind of standard or expected load profile for electricity usage, and there's the different days: a summer Sunday, a summer weekday, and then the same in winter. And these are very useful because then if you have different types of households in a particular area, you can actually predict, and in terms of planning, what's the kind of peak and off-peak and total usage or expected usage of an entire suburb or district or province. But of course, this is an abstraction and an aggregation. What typically happens is this is done manually by experts over multiple years, and it takes very long to update, like between 5 and 10 years to update these. And during that time, as we know, South Africa is quite it changes the socioeconomic conditions of households, change, they evolve, and so electricity consumption. So an entire suburb over 6 months could get electrified, or the income distribution of the households could change. So in this work, we explored how AI techniques can be used to automate the construction of these representative daily load profiles. And it was work done by Wipke Toussaint for a master's. And she was also, during her master's, she was a data scientist at the Energy Research Center. So this was it was extracting patterns from a very large data set. It was the DELM-H data set. And Wipke actually curated this data set, which was just released, I think, 2 or 3 years ago. And it had 3.3 million daily load profiles over 15,000, roughly 15,000 households over 20 years. So she designed an approach that combines internal cluster evaluation metrics. So cluster analysis, unsupervised learning. There's some domain agnostic metrics that are used to evaluate cluster compactness, distinctness, and so forth. These are these metrics: DBI, MI, and silhouette index. So they're quantitative and they're domain independent. So they'll give you the most compact and distinct clusters, but they do not take into account the application context. Whereas typically in real world applications, you'd want to look at certain properties or prioritize certain properties over others, depending on how you want to use these clusters. And these are usually, they're called external evaluation metrics. So as part of her work, she represented or designed something called a cluster scoring metrics. And it was done by interrogating and engaging with the domain experts. And she used competency questions to do this. And she came up with measures to evaluate and pick the best cluster set from the clustering activity. So if you just use these traditional metrics, the DBI, MI, and silhouette index, you got these kind of represented load profiles. And while they yielded the best values by the traditional metrics, you could see that they weren't really informative. Using her cluster scoring matrix, which used information entropy and had measures for expressivity and usability, she picked a different cluster set. And here you can see there's a bit more distinction between the load profiles. And they are more usable in terms of the application context. The overall approach is the daily load profiles were put through a cluster analysis. You use something called pre-binning, which was just the initial kind of partitioning of the data by total consumption, because that's the way the experts used it. They first put all the households in terms of their total usage. And then we did some experiments and came up with a whole lot of cluster sets. And then it was all those different cluster sets were pushed through this cluster set scoring matrix. And then the best cluster set, like the one that I showed you in the previous slide, was selected. It was then we used a classification, a simple multinomial regression, to map it to the demographic attributes so that we could actually map those represented daily load profiles to the characteristics of the different household types. And now that will yield the usable represented daily load profiles that can be used by the domain experts. So this is what the system produced. So this is the benchmark ones which the experts had produced, and was of course a bit outdated. And this is the one that her system produced. After some analysis, there were some minor issues or things that it picked up, which deviated from this broadly, but it was definitely usable by the experts. And of course, we've got ongoing work to refine that system. So the current and future research directions in terms of where we are heading with this work or this research, we believe that interoperability is mostly being dealt with. There's still lots of issues on the knowledge representation and reasoning, and specifically better mechanisms to acquire knowledge and to handle how knowledge evolves. The thing that's really interesting is automatic hypothesis generation. And this is what scientists do generally when they do empirical research. And we've done some initial work on that recently. And machine learning, of course, most of you are aware of how machine learning works. And the area there is to automate the hyperparameter optimization and the algorithm selection so that we can automatically build these machine learning models. And on the software engineering side, we still think architectures and frameworks, we need richer architectures and frameworks for these kind of next generation adaptive and cognitive systems. So this is just where we currently are at, and just to mention a few things here is that our current thinking is that these future systems have to be machine and human centric systems. So it's a cooperative endeavor between machines and humans. And this is now called Augmented AI. And if you're interested in that, there's this notion of digital twins, which you can go and read up about. And it's a very interesting notion, definitely worth pursuing in terms of Augmented AI. I mentioned the frameworks and architectures. You have all these AI techniques like deep learning and Bayesian networks and ontologies, and they solve a very particular problem. But if you're building these complex adaptive and cognitive systems, you'd want to incorporate a whole bunch of them into a coherent system, and that's what's difficult to do. Like, where do you fit them in, and how do they interact with each other, and those coordination mechanisms. In terms of that, we see the belief base being a combination of ontologies, the declarative, specifying the declarative domain knowledge, rules like we've used previously, and then the Bayesian decision networks. And of course, ultimately, what we want is to try and see if we're observing some bounded physical system, can we discover new knowledge, and can we automate that process of knowledge discovery. So some concluding thoughts is there's a very fine line between automation and intelligence. And I always say the things that computers could do 30 years ago, very simple tasks, when we think of it now, we're thought to be highly intelligent. And now things that we do, like, for example, the AI that you use in your GPS in Google Maps, that's quite sophisticated, but we do not somehow think that this is AI. So it's quite fluid. I've mentioned the humans working closely with machines. I believe that this is an area definitely worth exploring. And of course, the very interesting area, to what extent can we automate the knowledge generation process? Okay, thank you. And I think I'll hand over to Francesco.
Yeah, thank you very much, Deshen, for a very interesting talk. And in particular, thank you so much for...
Francesco, I think you're mute.
Sorry, can you hear me? Hello, can you hear me now?
Yes, Francesco, I can hear you. I was on mute, but Francesco...
Okay, sorry, I don't know. So no, thank you very much, Deshen, for the very interesting talk. And in particular, it was very nice to hear how one can bridge the more theoretical concepts with some really very nice applications. And of course, I would like to be first in line for the development of my own digital twin, so that I can send somebody else in Zoom when it is appropriate. I don't see any questions at the moment in the Q&A. But since we are not so many, I would like to encourage people just to raise their hand, and we can allow them to ask their question in person.
Okay. But meanwhile, people were just kind of asking in the chat, and there is a question in the chat which is related to the references. And the people are just curious, you know. Okay, so you're supplying already the reference.
Okay.
No, you supplied to panelists, not to... Okay, sorry, let me just... Can you send it to the panelists and attendees, because only we could see your answer? Yeah, perfect. Okay, yeah, that would be the answer.
Okay, thank you very much for that. Anybody raising the hand to ask questions? It doesn't seem to be the case. Then maybe let's give people a minute to think about questions. Yeah, and Deshen, you know, it was very nice to see the generic strategy from lots of sensors and agents to practical applications. Have you thought if there is any use of this technology in the context that we are living these days? So, for instance, for the monitoring of COVID outbreaks, for instance, or for the tracing of contacts of people that have been in contact with people infected by COVID. Did you think about possible application in that context?
Yes, so I haven't worked on it directly, but I was definitely contacted about this. And so the biggest issue, I think, was in South Africa. So of course, in the East, in some of the Eastern countries, I think like China and South Korea, this just happened. But the privacy laws are quite, there's some ethical issues around it. So these to do that kind of system, if people participate, was, the technology is there already, because it's a version of like what you do with Uber. Because Uber can track you, and Uber can tell you when you're near your driver and where your driver is. So you could, using that same technology, you could, and if everyone has their GPS on, because it uses a cell phone GPS signal for Uber, you could see exactly when people come into contact, and if you had an identifier for each person, then you could easily do a track and trace. But the privacy is a massive issue. Maybe we should use Uber. Yeah, it's interesting.
No, thank you very much. No, I thought so. So the constraint is more the regulatory laws than the technology. Yeah.
Yes.
Yeah, no, but that's okay. That's a tough one.
Okay, and there is a question in the Q&A from Ashley, and the question is: do you need to have a deep understanding of a certain domain to apply this type of research?
I see. No. That's a good question. So I don't. I really don't know anything about biodiversity or electricity usage. So I was quite fortunate that my students had this background, but you typically don't need it, because what you can do is just engage with domain experts. So the idea is that when you create these systems, you'd engage with the domain expert who can provide you with that background knowledge. And in the same way, I think computer scientists, they get trained, agnostic of the domain, but yet when they leave, they get development jobs at banks, at medical aid firms, and so forth. And they really then don't have the domain knowledge.
Yeah, but that, Deshen, that is exactly, that's a very good question for another reason. That, as you all know, NITheCS is now a very multi and inter and transdisciplinary institute. Yeah, so we will have lots of skills in NITheCS. Yeah? And for instance, you now have shared with us technologies, let's call them technologies, or software approaches to certain classes of problems, that some other people that are now in NITheCS might have without knowing your technology. Yeah? So the role of NITheCS, or one of the roles of NITheCS, will be to bring together people with different skills and know-hows, and start addressing very interesting questions that each of us on his or her own wouldn't have been able to do. Yeah. So yes. In that sense, I think your talk was very important, because I'm pretty sure that there are many classes of problems that that could be addressed with the technology that you described, with the methods that you described. Yeah? So that would be very, very important. Yeah?
So just on that note, and of course this was just some of the work that I've done, but another interesting one which might be interested I don't know if there's any astronomers around, but so some of you, if you're working in astronomy, will definitely know Kavilan from UKZN. And so I think a few years back, one of the projects was a cognitive system for astronomy. And it was based on a similar, the similar sort of architecture. So if you're interested in that, maybe speak to Kavi. So I I provide some input into proposal. Yeah, so it definitely has, as you said, Francesco, quite a wide range of application. It was the Swiss South Africa.
Ah, yes, yes, I remember that. I took part in one of those workshops.
Yeah.
You know, and I think there is, in the meantime, no, thank you very much for that comment. There's another question in the Q&A. I don't know if Ilya wants to guide us through that.
I can see it. Should I respond?
Okay, if you want, yes, please.
Oh, maybe do you want to just Ilya, or should I read it out, because maybe not everyone is seeing it.
I'm happy to read it.
Okay, yes, Ilya, go ahead.
You mentioned that domain experts responded better to the Bayesian networks than ontologists in the biodiversity domain. Might this be true for the rest? Might be this true for the rest of the domains of application?
Okay, and again, that's a very good question. These ontologies come up with these complex class hierarchies with properties, and it's based on how we think about declarative knowledge, concepts, and relationships between concepts. The Bayesian networks takes a different, it goes at a higher level. This is not at the concept level, it's at the causal level. And it's about how certain events or states of the world affect other states of the world. And it's got uncertainty that propagates through it. I have found, so I initially started with ontologies and thought that this was really the way to do the knowledge representation. And I found, without fail, the non-computer scientists, when I spoke to people outside of computer science, domain experts, they liked the Bayesian networks. And my intuition is that this may actually apply across different domains. And the reason is that the Bayesian networks, they follow this idea of bounded rationality. So what they do is, when you're making decisions, you immediately have intuition of what is important. So you don't ever look at the complete state of the world. It's impossible, because then you're going to have a million things that you have to take into consideration. But you pick the top 5 or 10 things in your decision making, and then you structure and organize them, and you then abstract all the rest out. And that kind of what they call belief propagation or uncertainty propagation is, I think, a lot more intuitive to people who make rapid decisions. So I would agree that Bayesian networks might be more universally accepted and adopted.
Yeah, thank you, Deshen, for that. Sorry, I see, so there are a few new messages in the chat. There's the question to me, yeah, how quantum machine learning will depart from this picture. Yeah, I mean, not very much, because quantum machine learning is just another technique to do machine learning. You just use a different hardware. Yeah, so the general strategy will be essentially the same, I guess. Yeah. And even in the quantum domain, there are models for intelligent quantum agents. Yeah? And in fact, we had a talk on that probably a few months ago. It was Professor Milburn from the University of Queensland who spoke about agent system in the quantum setting. And so, and if you're interested, you will find it in the YouTube channel of NITheCS. Yeah? But I think this will be a topic of another talk. Yeah. Sorry, Deshen, there is a question in the chat asking for a reference for the use of cognitive systems in astronomy. Maybe we can provide, if you have it in your head, you're welcome to type it in the chat. Otherwise, we can distribute it later to the participants.
Unfortunately, is that I was supposed to be a part of that grant and project with Kavi and a few other people, and I just didn't end up doing anything. So I would say contact Kavi and maybe through Francesco.
Yeah, okay. We will make an effort to find the reference and share it with Tembiso. Yeah, I will make a note of Tembiso's name. Yeah, okay. Then if there are no more urgent questions, Deshen, it's my pleasure to thank you very much for a very engaging talk. You heard it from the questions. There was lots of interest and hopefully many more applications for your techniques and for your approaches. So thank you very much for that. And thank you to all the participants who were with us this afternoon, although we are all aware that some horrible things are happening out there. And so be safe when you go back home, or if you're not at home, yeah, because there's not only COVID out there at the moment. Yeah, there are also other dangers out there. Yeah. So Deshen, thank you very much for your nice talk, and I'm sure that in the near future we will find another opportunity to invite you to share some other interesting artificial intelligence related skills with the NITheCS community. So thank you very much. Ilya, thank you to you as well for moderating the questions. Yeah, no, thank you very much, everyone, and please stay safe. Yeah, thank you.
Thank you, Francesco.
Thank you, Deshen. It was really very nice. Thank you very much.
Okay.
Thank you. Bye-bye.
Bye.